So thanks very much for being so early today. I know I'll be the first one to present. Thanks for the organizers. It was great to come here. This talk is about a vulnerability that I discovered in 2017 while I was designing with other people the Woodstock sidechain. And somehow it's a vulnerability that comes over and over again to hunt new projects. And so it's important to refresh it and make sure that we know how to mitigate it because it's still there in the big control. So the agenda for this talk, and I'm going to try to make it fast. I'm sorry, but a lot of things to talk. We'll talk about SPV clients and Merkle tree basics that you probably already know. The first vulnerability that was found in 2012 on the Merkle tree, the vulnerabilities that I found in 2017, how I found them and how those affect specifically Woodstock and some other sidechains. A third vulnerability and how can we fix this? Like if we had to do a Bitcoin hardware, software, and if we can't do any of these, how should we protect bridges and sidechains from this vulnerability? So basic concepts that again probably people here already know. What is an SPV node, or sometimes called a lightweight wallet? It's a node that participates in the network that follows the chain with the highest cumulative work. So it does not validate all consensus rules, just enough to follow this chain. And will only verify certain subset of transactions of interest, probably transactions that are income payments. It will require a huge number of confirmations to be sure that these transactions are actually valid. And it makes use of this transaction registry. So there is a debate over if this is secure or not. But the real thing is that all the bridges, zero-knowledge bridges, optimistic bridges, sidechains, all make use of this data structure. So, we like it or not, it's useful, it's used, so we must protect everyone from the vulnerabilities that it has. A single first concept that will help us in the whole presentation. There are three kinds of transaction validity checks that one can perform. The first one is obviously that the transaction is syntactically valid, which means that the fields are correct, I can serialize and deserialize it easily. The second is the semantic checks that the full node does with the transaction, which means that I can connect this transaction to the blockchain and it checks all the context things, like it does not perform double spend, it does not create money where it shouldn't. And then there is a set of rules that only SPV nodes check. And the important thing of these rules is that they are not defined. Like you can choose any subset of the rules, and depending on the subset of the rules you choose, you could have certain problems or flaws. So first, what is the Bitcoin Merkle tree? It's a structure, authenticated structure, where in the leaves we have the transactions, and in the middle nodes we have a 64-byte chunks that are composed by the hash of the left child and the hash of the right child, and the hash function that combines the two hashes into a planet hash is the SHA-256 squared, applied twice, as always in all the Bitcoin code. This function is applied twice. So kind of simple, maybe too simple, but it provides a super interesting property, which is that you can create an inclusion proof, logarithm in size. So basically, you take the transaction you want to prove that is included in this data structure, and you provide all the complementary hashes, or sometimes called sister hashes, and you combine them until you get to the root, and magic, you have a proof a secure proof that a certain transaction is included. So everything is fine, but it's not. So the first problem that was detected in 2012 was that this data structure, what if the number of elements is not power 2? Well, what if I have something that I cannot pair with? And so what one should do? So Satoshi thought, okay, let's duplicate the last element. It's always one element that I have to duplicate. each level. So for instance, in this tree, the node F, because it doesn't have any other transaction 7 and 8 to combine with, it just duplicates the hash of F. And so someone discovered that by doing some trick, you can actually create two blocks that are syntactically valid, both of them, but they essentially contain different information. Like for instance, in block Y, we have only 6 transactions, and they hash to node A, but in block X, we actually added 2 more transactions, which are a copy of the last 2 ones. So we have transaction 1, 2, 3, 4, 5, 6, and then we put again 5 and 6. And if you check, you will see that obviously you get the same hash, right? So terrible bad here. So what can you do? What could you do with this thing? So there are a lot of attacks you can do with it, but let's just focus on one. So let's say I'm a miner, I have 15% of the hash rate, and I choose, let's say I can connect directly to the remaining miners. It shouldn't be so easy by exploring the Bitcoin graph. So let's say I identify 10% of the mining network. So I will, every time I create a block, I will create 2 versions of this block. One is malleated to be syntactically valid but semantically invalid, because of course, if I take a block having repeated transaction, that is a double spend, so it doesn't work. So I will send the back copy, the X, to the 10% and the Y to the remaining 75%. And what will happen is that what used to happen in that code is that this 10% takes the transaction, it says, okay, it's invalid, and it, because it's semantically invalid, and it would mark it in the cache as invalid. Like for everything that block is invalid, that block hash is invalid. So whatever happens to the other part of the network, this miner will never follow that chain again. So then this malicious miner can perform again the same attack. So it chooses again a new 10%, and it does the same with the next block and repeats it. And finally, what you have is that you would have, after 8 iterations, you have 8 groups of miners, each one mining a block, a chain of different length, but everyone is incompatible, so everyone is isolated, and you have 15%, so you actually have 100% of the effective hash rate. So you put everyone out of business, and you are the sole miner, and you can do this very fast. So how did the core developer first? This is very interesting. This is the largest comment in Bitcoin core code. Like, they put a warning and they draw this beautiful ASCII chart of the tree because they knew that someone would make a mistake in the future if they didn't do that. It was not enough just to correct it. So they put a huge warning there talking about this vulnerability. And how did they correct it? Well, basically, if you submit a block that has repeated transactions, instead of considering it invalid, it adds a new type of result, which is the localization result, block mutated. And if the block isn't mutated, it will mark it and insert it in the cache to make sure that it doesn't check it again. But in case it is mutated, it just let it go. So if it comes again, it will be fully checked again. Okay? So no optimization you can do with these mutated blocks. But then, while I was working on Rooftop, I had this idea of, we have these 64-byte chunks that are the middle nodes, and we have the transactions that leave that have variable size. Eventually, they would also be 64 bytes. So what if we could interpret a middle node of this tree as a transaction? Or the opposite, what if we could add a new level to a Merkle tree, assuming that we can convince someone that a transaction is actually a middle node? Okay, so anyone that relies only on Merkle intrusion proofs will be fooled by this idea. So the basic problem here is that there's no distinction between hashing a middle node and hashing a leaf node. This is sometimes called domain separation of the hash function. In cybersecurity, it's called type confusion attack, where you basically can feed someone with a data that is from other type. So the important thing is that if I do this, I keep the root hash. Like I could create two versions of a block that also have a root hash, the same root hash. For instance, in this example that I have in the right, I have a block with two transactions, and then I have a block with a single transaction, and I just want to make these two blocks have the same hash. So the question is, can I do that? Obviously, this transaction should be exactly 64 bytes in length. Okay? So from now on, I'm just going to rotate everything. Like instead of considering a node having a left part and right part, I will rotate into the left part on the upper side and the right part on the bottom, because it's easy to display how the fields fit in this 64-byte chunk. But remember that it's just rotate it and you will see clearly that it's part of the memory, right? So this is how a 64-byte transaction would look like if one really wanted to compress a transaction. So what we can see in different colors is that most of the parties will be used by the hash ingest of the UTXOs that we consume. Part of that lies in the first chunk, which corresponds to the left side, part in the right chunk. And we can also see that we only have space like for 4 bytes of script pub or scriptc. Like we could eventually move bytes between them and still have the same size. But with 4 bytes, we cannot input a page-to-script cache, right? So this allows us to create a syntactically better transaction, probably a semantically better transaction too, but not really to force someone to believe this is an incoming payment, right? So again, this is in the left is how I will show the 64 chunks, and in the right you see how this is rotated and how the first part goes to the left. The left should be the left hash and the right part should be the right child hash. Okay, so first of all, let's try to, for the first attack, we want to replicate the attack that people did by adding repeating transactions. We want to do the same attack now with the 64-byte transaction. So we want to create a 64-byte transaction that is only syntactically correct. We don't need to be semantically correct, just enough for the node to receive it, to evaluate it, and to mark it as invalid. So it turns out it's very easy. Like we only have 4 fields that we need to have specific values, like the input count, the script length, the output count, and the output script length, and it's done. Okay? So can we do this? Yes. Essentially, we want this to be each one of the sides. We want to be the hash of certain transaction. Okay, so we have to kind of iterate many left side transactions and right side transactions until we get one hash that has the conditions that we want, right? So for instance, in the left side, we only need to test on the average like 256 times, and we will get this specific pattern. And on the right side, we need to match 3 bytes that are constrained, so it will be about 2 to the power of 24 times on average. So it's kind of easy. So what happened when this was reported to the Merkle court? They said they did something. First they did it wrong, and then they realized they found another problem, and then they realized that the only way to solve it forever was avoid caching anything about invalid nodes, right? They say, okay, we had this malleability problem in 2012, we have this again, the same problem in 2017, and we are not going just to fix this another kind of mutated transaction so that in 2 years we have a new kind of kubernetes of the same kind. So again, they put a huge warning here in this processing block, and what they actually do is they check fully the block, and they just only call accept block, which is the one that can eventually cache anything, only the block is fully valid. Okay, so no way of if they don't somehow refactor this and forget about this, there's no way that this kind of vulnerability is coming. But now, let's say that I want to create not a syntactically correct 64-byte transaction, but semantically correct. I really want to fool someone giving a Merkle path to a specific middle node to convince them that I'm sending them money, right? Bitcoins. So we have a huge problem. Like in the left part, we have 230 bits that are constrained by this UTXO hash. So it would be impossible to create a valid block that has a left transaction that hashes into that part, right? So we have a problem. And on the right side, we have 112 bits that are constrained. And the problem that these are constrained is mostly because these 5 bytes that are the yellow one that are part of the UTXO hash that lie on the second part. Okay, so now is when I really found a way to make Roostok at that time when we are designing vulnerable to a new attack. And so I'm just going to give a brief introduction of Roostok so that you understand why Roostok was susceptible to this attack. So Roostok was the first sidechain launched in 2018. It is merge mining Bitcoin. It has a 30-second block time. It's secured by more than 51% of the Bitcoin hash rate with merge mining. It has a hybrid SPV federated HSM enforced to a pen. It seems like complicated, but it's easy. I'm going to show you how it works. The pen is drive generated, so I don't know what will happen with drive chain, but if the community goes and try to implement drive chain, Roostok will be the first chain to use drive chain. It's EVM compatible. It has a very rich DeFi ecosystem where we have Bitcoin collateralized stable coins, lending, borrowing, all kinds of this crazy stuff. And the native token is Bitcoin, and it has always been and will always be. There's no other subsidy, there's no other, users could create their own utility tokens, but essentially it's Bitcoin only. So this is how the bridge works. So when you want to pay in, when you want to send funds to Roostok, you actually send funds to a multi-sig that is controlled by HSM devices. And these HSM devices, each one runs a node in this mode. So these devices actually are autonomous. No one can extract a private key or anything. But if that is not enough, if you really want to begin, because this is a decentralized process, you have to inform a smart contract on Roostok that you have performed this begin. And this is where the SPV proof comes. The Roostok has a smart contract that has an embedded SPV client based on Bitcoin J, the original code. And so you send the transaction, the Merkle path, all the 100 blocks. You need to send 100 confirmation blocks to the Roostok blockchain. This smart contract takes everything and says, okay, this is a good begin, this is valid, and then releases the RBC. So it's very important for us that this node cannot be fooled by sending some other kind of data that is not actually a valid, semantically valid Bitcoin transaction. So let's say that what I mentioned before, we want to create a fake transaction out of a node that is not actually the leaf node. So this fake transaction is what we actually want to Roostok to believe is a penny. Okay? So the problem here is that I only have 4 bytes, as I mentioned, for the script part, and I won't be able to feed the multi-sig address of Roostok there. So it's game over. This does not work, at least for Roostok. So the interesting thing, even if this does not work for Roostok, is just a month ago, I found out that there is another bridge, very well-known bridge, that uses a different set of SPV client validation rules because they are not standardized. And what I found in this client is that the client does not check that the transaction has any, because most SPV clients do not need to look at the input, they just need to look at the outputs, because the input they cannot verify, right? If it's a double spend or not, they just return it. So Roostok code verifies that actually there's at least one input, because that is a big consensus rule, but this other bridge did not verify anything. So you could just throw a transaction having no inputs. And what I found is that without inputs, if you don't put inputs, then you have a lot more space to put the address of the pegging, and you can put it just in the middle of the first chunk and the second chunk. And by doing so, you don't actually have to brute force all the 160 bits, because some lie on the left side so it can be brute forced separately than the right side, right? So makes this attack easier. It does make it practical, but it's important to realize that you can always make things worse. So if you want to attack this, you would need to brute force. The worst part is the right side, which you would need to brute force 122 bits. Probably someone can optimize this. Just not so important for me because it was fixed. But yet, you can always make things worse with this vulnerability. So now, this is the one that affected Rushdo. This is one that was really interesting. So we evaluated what if we could try to make a node a transaction. Let's try to do the opposite. Let's try to fool someone into thinking that a transaction that is a semantically valid transaction in an actual Bitcoin block is a middle node, and there is a fake transaction that is actually a left child of this node or a right child of this node. So again, what I need is to create a valid 64-byte Bitcoin transaction, semantically valid, with certain properties. So what are the properties that I need for this transaction? So in the left half I have these 230 bits that are constrained. Basically, I can do nothing. I wouldn't be able to create a child of the left part. So I only have the right part. And so it seems like, okay, so there are only 112 bits that are constrained, right? Maybe it's possible. But there is a trick that I found here, is that you see that the first 5 bytes in the second chunk are still part of the transaction hash, the UTXO hash. So instead of trying to brute force them, like instead of thinking them as constrained, let's put anything there. Let's remove them. And now I have a lot less bits to try to brute force, because I can do a trick, and then afterwards, if I find a transaction that matches these color boxes here with different specific values, then what I can do is now I can try to find a transaction by brute forcing that ends, whose hash ends with those 4 bytes, 5 bytes, which is very easy because it's only 2 to the 40 bits, right? So eventually, if I make an average of 2 to the 40 tries, I will end up having a transaction whose hash, which hash is ends with this pattern, arbitrary pattern that I found. So basically, the trick is we first do a first stage where we take a fake transaction, and this transaction can deposit million bitcoins in the sidechain, whatever, it can be of any size. So I'm free to do whatever I want in that transaction. I hash it and hash it over. Maybe I change a bit or a block time or anything that's easy for me to rehash it and rehash it. And if I do this as many times, this varies because there are speeds that you could try to constrain or not, like the amount, for instance. But essentially, approximately you can try, in average you will try 2 to the power of 72 times, and you get to the right part. And then in the second stage, you just try to find a transaction that ends with those 5 bytes that I mentioned, whose hash ends, and you put that in the blockchain, and you're ready to attack, right? But we still have a little problem, is that transaction that I call T here, that is the one that is 64 bytes. First, it needs to move a lot of Bitcoin, because to make room for more unconstrained bits, to get more constrained bits, we have to move higher and higher Bitcoin amounts. Because the amount is one of the fields that we are constrained. So the more Bitcoin we want to move in this transaction T, these Bitcoin are not used for the attack. Just to be able to have more unconstrained bits, the better and the faster we can do the attack. But the problem is that, as I mentioned, this transaction T cannot consume a standard script, standard Bitcoin address because it's too small, and cannot produce a standard Bitcoin. Cannot be, have a script path for a big standard Bitcoin address. So if I move Bitcoins in that transaction, I probably will lose them. Like anyone will be able to take them. So I have to do some trick. If I'm a miner, I will sandwich this transaction T with the transaction P and E. P will be the transaction that leaves money on the table for transaction T to be consumed, and E will be the transaction that consumes the funds that are linked on the table by transaction T. So I'm done. I will put a lot of mining extra capital value in. So someone could try to revert this transaction. Yes, that possibly, maybe they don't realize this is happening, or I can try to mine selfish mine many confirmation blocks to avoid that. But you can do this. And then we put R, which is our fake transaction there. And what is also interesting is that since the huge preprocessing part, I only have to do once, and then I can repeat this attack as many times as I want. Okay? So 2 to the 72 power is a lot of work, right? But if you think about it, the Bitcoin network does approximately that amount of work every 10 minutes. So it's a lot, because but it's not a lot for Bitcoin ASIC. So one of the questions that I had is, what if we repurpose a Bitcoin ASIC to do this work? So at first, there seem to be very, very different problems. Like in one, I have to hash a transaction many times until I get a certain hash. And the other, I have to hash a 80-byte block header. But if you take a look at the mapping of the fields and you compare that to a transaction, then you actually can make it fit, kind of, right? So what I realized is that you cannot create an 80-byte valid transaction having a pay-to-script hash, because that would take 83 bytes. So almost I could do that, like create a transaction and map directly to a Bitcoin header so that I can brute force like the transaction instead of the header. It could be possible, but no, it's not possible. But what I can do is I can have 64 bytes more and create a transaction that's 144 bytes, and then I have a good magic in there. There is a little problem here, matching that, is that the SHA 2056 has a padding, and that padding contains a field, and that field is the size in bits. So since I added 64 more bytes, then there is a bit there that changes. It's highly probable that the current Bitcoin ASICs, they do not allow you to change that because they are single purpose, but it's not a big deal. I mean, you could manufacture a chip that has this possibility of switching that bit. It's the same amount of work or space almost. So basically, you could do that. Another problem trying to match an ASIC with this setting is that an ASIC will try to find this hash that ends with a number of zeros. And I say ends because the Bitcoin hashes are reversed in the hardware. So basically, that will overlap the log time, and I don't need to fix. I don't have constraint bits in the log time. So it actually does not help me to find a hash that starts with zeros. But it could be very easy to change the mask that the hardware does to check for the solution. Okay, so for instance, here in the code I have an FPGA that what it actually does is it takes the first bit or the last bit, sorry, and it checks that the fourth bytes are zeros, and then it's a mean solution. And we can actually change the mask here. Instead of the last 4 bytes, we could put a variable mask in the hardware so that we take some other bytes in this 32-byte thing and check that those are zeros. So you see that it's very, very easy to repurpose. If you are going to do a tape out of a new chip, then it's very, very easy to make it that can do both things. Okay, so this I did recently. I tried to estimate the cost of the attack based on the latest mining chips. And well, it turns out that if this ASIC already existed, like if there was an ASIC that allowed me to do these little changes, then renting an ASIC from the hardware would cost just as low as 10K if someone would be able to rent me that. Buying the ASICs is just 100K, and creating the ASICs is obviously the takeout cost is between 10 million and 20 million. So yeah, I think it's but if you are going to tape out a new chip anyway, then you could put this in the chip, right? So what are the potential solutions? So let's start with a solution that will never happen. You could change the Merkle tree hashing method so that you add a prefix 1 to middle nodes and a 0 to leaf nodes, and you're done. But nobody's going to do this because it's expensive and contentious to do hard forks. So what can we do with soft forks in Bitcoin? Well, the easy thing is just to make a transaction that consumes 64 bytes or less invalid. I think it's so easy, like just one line. But there are other potential solutions, which is adding a new field to the block header. Let's call it Merkle depth, that is has 4 bytes. And you could put that in the version field, and it will tell you the depth of the tree just before anything. So it will be very easy to see if you are doing the wrong leaf level for a simple transaction. But again, soft forks might happen or might never happen, and there is no huge interest for soft fork Bitcoin for this. So bridges take different protective measures. The one that Rootstock does is very simple. When you give it Merkle proof, it will check that the complementary hashes, the sister hashes, are not syntactically valid Bitcoin transactions, and the probability that it happens at random is 2 to the minus 56. So it's highly probable that by chance you get to a node that is actually a valid Bitcoin transaction. And so that's how Rootstock is protected. I would say that it's not perfect, but it works. If some time in the future, by chance, this happens, like a node in tree is a valid transaction, and there is a plugin just below it, then you could eventually create a hard fork on Rootstock and allow this to be processed, right? Obviously with the community. Okay, so this is how the Rootstock code checks. I'm going to skip this. It's in the partial Merkle tree class. And another solution for bridges, and this is implemented in one of the bridges, is to check that the Coinbase Merkle proof has the same length as the transaction Merkle proof. Because, as I told you before, you cannot create a left extension, like a left child of the Coinbase that is valid. Because in the left part, you have a lot of zeros to match, right? The Coinbase transaction is filled of zeros in the left part. So if I give you a proof, Merkle proof of the Coinbase, and I give you then another Merkle proof of the transaction that I'm really interested in, then that's enough. Because if we both have the same depth, then you are sure that there is no attack. And there is another interesting trick you can do with that, because the Coinbase transaction can be very large. Like if this was mine, like kind of decentralized, you have hundreds of outputs. So what you can actually do is take the mid state, because the SHA-256 is a Merkle Democrat construction, so you can take the mid state before you finish the hash, and you take a look at the bit fields, which in the feeding part, and you take a look at that field, and if it says that it has 512 bits or more, it means that what you have hashed has more than 64 bytes. So with a fixed amount of space, you could actually test that this is actually not a 64-byte transaction, and you're done. And this is the solution that nobody is using, but it's the one that I like best because it's the simplest one. I had this idea many years after I found the vulnerability, and the idea is that since the right part you cannot brute force, like you cannot create a pre-image of that, then instead of giving, in the left side I have a Merkle proof, typical Merkle proof of a user transaction. What if instead of giving you these complementary hashes for the first node, I give you a pre-image of the right part, right? So in blue, this function S is not a double SHA-2056 by a single 2056 hash. So I make sure that that part is fixed in size, it's 32 bytes. So by giving you that complementary hash in this Merkle proof, I'm secure that there's no way I could have used this middle node this middle node is not a valid transaction. So yeah, this is the easy thing. Just a little change in how we handle the Merkle proofs in here. And it's curious that it's helped by the fact that Satoshi chose to do double, double function, double SHA applications, right? So most of the which that I know are already protected. Rootstock is protected by this middle node check, and TBTC is protected by I don't know how it is protected, but at least authority found that they were not and they reported it. InterBTC is protected by checking the Coinbase net. And Liquid, it's very funny what Liquid does, but it protects Liquid. Every time you do a PV, it will, by RPC, it will call the Bitcoin core node and it will ask the number of transactions that block has, and it will check that the logarithm of that value matches with the Merkle proof that is given. So it performs an RPC call every time we process a paying transaction, which could be an service attack, I don't know, vector, but kind of weird, but yeah, it's protected. These are the links. There is a very, very cool explanation of the whole set of attacks that I have not created, but another person did. These are the links, but I will post them in my Twitter account. Sorry, I don't have Nostr yet. I know that everyone here has Nostr account. Not yet, but maybe today. But yeah, I will post these links if you want to learn more. And yeah, I came here sponsored by the company I work, which is IO Labs. And IO Labs has a grant program, 2.5 million grant program for developing anything you want on the Rootstock sidechain. So we are happy to scan this and participate. And there is also a Bitcoin Olympics hackathon for creating anything you want on Rootstock. And scan the QR code because I think it's starting soon. Okay, thank you very much. I'm not sure if I run out of time or. Okay, so time for questions or? Yeah. Okay, so if any question, I'm happy to answer. If not, thank you. Okay, thank you very much. Oh yeah, one question. Great.
So yeah, I noticed in the Liquid approach that they do gRPC calls to the node. I mean, if given all of this and you're operating the bridge, why not just create an SPV and run a full node and query against that?
Well, why not? What? Sorry.
Run full nodes instead of use SPV.
Well, there are systems that cannot run full nodes because they cannot go and connect to others. Like in Rootstock, like we don't force the users to run a Bitcoin full node together with the Rootstock node. So everything happens inside an isolated smart contract that doesn't know anything about RPC connections or peers or anyone. So it's kind of an isolated autonomous system that checks the SPV rules. So yeah, if we had designed Rootstock to kind of force you to run a Bitcoin node, yeah, we wouldn't have any of the problems. And actually, there is a paper that I posted 4 years ago called sync chains, which basically shows you how to do sidechains when you have these two nodes that you can run together. And there's a lot of problems that just go away. Like breaching is so much easier from the point of view of security. The paper is called sync chains.
Sync chains?
Sync, like synchronously.
Oh, sync chains.
Yeah, because these two things are synchronously cooperating.
Right.
Yeah.
Quick remark that the idea of restricting 64-byte transactions has been proposed as the great consensus cleanup software by Merkle like 6 years ago, which nothing happened. But the idea is out there. I don't think it's super controversial.
No, it's not controversial. No.
Yeah.
Yeah, no. I mean, no, it's impossible to do anything useful with a 64-byte transaction. So it's not controversial. It's not as important. I mean, there are a lot of things that seems to be more important at this point, but not controversial. Yes. Okay, thank you very much for coming this early. Thanks again for doing that.